You might think that when you sit down for a holiday dinner, you are so hungry that you could eat everything in the universe. But you cannot, because you are not a black hole. Black holes might be the hungriest things out there, consuming everything that comes close enough to get sucked in. But does that mean that we should be worried about them? The short answer is no. Here's the long answer.
26,000 light years away, a supermassive black hole is spinning at the center of our galaxy. A black hole as wide as the orbit of Mercury. A black hole more than 4 million times as massive as the sun. And everything in the galaxy is swirling around it. So, does that mean that the black hole is dragging everything into it until there's nothing left, like a cosmic drain in the great space bathtub that we call the Milky Way? In short, no. Black holes have gotten a bad rap, so let's set some things straight. A black hole is just an object that is so dense that as you approach it, the velocity you'd need to break free of its gravitation, known as escape velocity, exceeds the speed of light. This means that within a certain distance from the center of the black hole, not even light travels fast enough to escape. And nothing can travel faster than light, so nothing can escape. And while that might sound a little bit terrifying to you, the first thing you should know about our resident black hole, which is named Sagittarius A star, is that it's not terribly big for its kind. Black holes are generally divided into two classes that are hugely different in size. First, there are stellar mass black holes, which have the mass of several to maybe a few dozen suns. These are formed from supernova explosions of giant stars at the end of their lifetimes. Then, there are supermassive black holes, which include the one at the center of our galaxy. Astronomers don't know for sure how supermassive black holes form, but ours is actually pretty small, with just 4 million times the mass of the sun, compared to those at the centers of some other galaxies which are more than 100 million times the mass of the sun. So that makes our black hole sound nice and non-threatening, right? But the much more important fact is, a black hole's gravity doesn't just suck things in like some sort of cosmic vacuum cleaner. Most things in our galaxy are so far away from it that they barely even feel the black hole's gravitation. In fact, here on Earth, the gravitational pull of a person standing 30 feet away from you is 10,000 times stronger than the gravitational pull of our galaxy's distant supermassive black hole. And even objects that are a lot closer to it will most often just fall into an elliptical orbit around it. So the fact is, our galaxy is orbiting Sagittarius A star just like we're orbiting the sun, but we're not getting drawn into it. But I'm not saying that hanging out near a black hole is going to be pleasant or even comfortable. In fact, I don't recommend it at all. This is partly because of the effect created by clouds of gas that form around black holes called accretion disks. These disks of gas become superheated, producing strong emissions at X-ray and radio wavelengths. So in the immediate area of a typical supermassive black hole, there is a lot of rather unfriendly high-energy radiation flying around. And another concern, if you happen to find yourself in the metro area of a black hole, is tidal forces. These forces are exerted because one side of a body, like a planet or moon, is closer to the massive object than the other side. That closer side feels a stronger gravitational pull than the far one does, and the closer that body gets to the massive object, the bigger the difference becomes. Eventually, this difference becomes so great that it causes the body to start stretching out. Now, the boundary that stakes out the maximum danger zone around any black hole is its event horizon. This is the distance from the center where the escape velocity equals the speed of light. For our black hole, the event horizon is about 30% the average distance between the Earth and the Sun. So outside that range, an object orbiting the black hole would be far enough away that the tidal forces wouldn't do too much harm. But if the object manages to cross the event horizon, then basically all bets are off. The side that's closer to the black hole would begin to accelerate faster than the farther side, creating an inescapable stretching force that physicists rather delightfully refer to as spaghettification. So yes, if you found yourself inside the event horizon, your noodle would essentially be cooked. Nonetheless, you don't have to worry your intelligent little head about any of that, because our galaxy is orbiting Sagittarius A star. You can rest assured that the sun, the Earth, and everything else is going to keep on turning, blissfully unaware of the supermassive black hole at the heart of our galaxy.
I don't know about you, but I always feel better after watching that video. There's a soothing feeling that comes from the knowledge that it is very unlikely that you will be sucked into a black hole tomorrow. But just in case, you can always arm yourself with some knowledge. So here's some of the cool ways that those black holes could form.
Do you think you can make a black hole out of light? That might sound like a trick question, or like something right out of the Shower Thoughts subreddit, but physicists say that it should be possible to create a black hole out of nothing but light, called a Kugelblitz, after the German word for ball lightning, even though they have no idea what would actually happen if you tried to do it. Before we talk about that, though, let's talk about the more standard black holes. Usually, a black hole forms when a lot of matter is packed into very little space, which increases its density. If the matter is dense enough, the gravity at its surface becomes so strong that nothing, not even light, can escape its clutches. So to make Earth into a black hole, you would have to compress its 6 trillion kilograms of rock and water and metal down into a sphere with a diameter of just 16 millimeters. That's how dense I'm talking about, but we're just getting started here. Einstein taught us that E equals mc squared. In other words, that the energy stored in a bit of matter is equal to its mass times the speed of light squared. This means that there are huge amounts of energy in tiny bits of matter, like atoms, which is the basic idea behind nuclear power and nuclear weapons. It also means that energy can sometimes act like matter. Now, light doesn't have any mass, but it does have energy. And thanks to E equals mc squared, gravity can't tell the difference between energy and matter and pulls on them both. And this raises an interesting possibility. All it takes to make a black hole is to pack a bunch of matter into one place, and gravity treats light just like it treats matter. So you could, theoretically, make a black hole out of nothing but light. A Kugelblitz. Creating a Kugelblitz would take a really incredible amount of light, though, because now we're working with Einstein's famous equation in the opposite direction. Before, we had a tiny amount of matter producing a huge amount of energy. Now we have to supply a ton of energy in the form of light for it to act like tiny bits of matter. So let's go back to that hypothetical black hole with the mass of Earth. If we wanted to make the same black hole out of light, how much light would we need? All of the lights on Earth? All of the sunlight that hits the Earth in a day, in a year? What about all of the sunlight put out by the sun over the course of an entire year? Not even close. To get an Earth mass Kugelblitz, we would need all of the light put out over 10 years by all of the stars within 350 light years of Earth, all squished into a bit of space the size of a mosquito. Okay, that's a lot of light. But what if we wanted to make a black hole that was way smaller, like, I don't know, with the mass of a big cruise ship, like the Titanic, about 50 million kilograms? To make a Kugelblitz that small, you would need to squeeze all of the sunlight that hit Earth last year into a volume 8,000 times smaller than a proton. It is hard to imagine how so much light could get shoved into one place, or any sort of technology that could accomplish even a fraction of that in the foreseeable future. But even if it could happen, there is another problem. Making a Kugelblitz means that you have to pump so much light energy into such a tiny region of space that it would get really hot, since heat is just a form of energy. We're talking hotter than the universe was 1/100th of a millionth of a trillionth of a trillionth of a trillionth of a second after the Big Bang. And at that extreme temperature, physics as we know it sort of stops working. Space turns soupy, gravity is nonsense, and we have no idea how to describe anything. So if space gets that hot, gravity might go haywire and not be able to form black holes at all anymore. Or maybe gravity would get super strong and form a black hole with 1,000,000 times less energy than we think it should take right now. We just don't know. We might never know. For now, it seems like Kugelblitzes might be theoretically possible based on Einstein's basic equations relating energy and mass. It's a cool idea, using lots of highly focused light to create a black hole, something that even light can't escape from. But we have no idea how we or the universe would make one, or even if there's some undiscovered law of nature that forbids it from existing.
It's a little meta to think about a masochistic light that forms a black hole that other light can't escape from. But hey, black holes are intense, and if you thought the Kugelblitz is intense, you will want to watch Reed's video about some other, maybe even more extreme black holes.
Black holes are some of the most extreme astronomical objects out there. They're dense enough to pack the mass of the Earth into the size of a marble. And at the heart of each one is a point of infinite density where space and time cease to exist. But even among these extreme objects, there are extraordinary ones. We're talking black holes that grow larger, consume more, and spin faster than all the rest. By finding and studying these outliers, astronomers get a glimpse of physics at its limits. Here are 3 of the most intense black holes, helping them do just that. The most massive black hole astronomers have directly measured is located 825 million light years away in the galaxy Holm 15A. It weighs in at around 40 billion solar masses, but it didn't start out that big. To reach its mass, it had to consume almost all the matter around it, leaving basically a ghost town around its galaxy's center. According to a study submitted to the Astrophysical Journal in July 2019, this likely happened when 2 black holes merged. As they danced around each other, whatever matter they didn't devour got ejected out of the region. Now, while this whopper holds the current record, pinning the blue ribbon on the most massive black hole isn't an easy job. Since black holes swallow up light, we can't directly see them. which means astronomers have to get creative about their measurements. They got this one's mass by looking at how its gravity pulls on nearby stars. But they can also use less direct methods to gauge the mass of a black hole, like looking at the spectral lines, or chemical fingerprints, in the light surrounding it. The shape of those lines can tell them how fast the source of that light is moving. This method is less precise, but scientists used it to measure one black hole that might be around 66 billion solar masses, and another could be as much as 100 billion. It's hard to say for sure how accurate these measurements are, but regardless of whoever ends up with the crown, all of these objects will help astronomers figure out if there's an ultimate mass black holes can achieve, because we're not actually sure about that. The next type of extreme black hole consumes an enormous amount of matter. Most supermassive black holes, including the one at the center of our own galaxy, are kind of lazy. The occasional morsel might fall to its doom, but for the most part, stuff orbits far enough away that they barely eat anything. There's a small group of them, though, literally the 1%, that astronomers call active, meaning they're constantly gobbling up matter around them. We find this type of black hole in a region called an active galactic nucleus, or AGN. The AGN contains the black hole, its accretion disk, and the surrounding donut of dust and gas. As these black holes devour matter, the AGN emits light, in some cases outshining all the stars in the galaxy. The hungriest black hole ever detected fuels an AGN around 12 billion light-years away, in one of the oldest galaxies we can detect. It devours a mass equivalent to our sun every 2 Earth days, and it shines as bright as 700 trillion suns. For comparison, if this thing were at the center of the Milky Way, we could see it as a pinprick of light shining 10 times brighter than a full moon. And that's about twice as luminous as typical AGN. This discovery was so surprising that the team of astronomers that found it had to check that the brightness they detected wasn't exaggerated by any other phenomena. For example, many AGNs have bright jets of particles streaming out of either side. But follow-up research suggested no jets, and nothing else that could be boosting the signal. So it looks like this AGN is just naturally brilliant. The third extreme black hole is the fastest spinner. That prize goes to the black hole known as, well, this. And it's located in our very own Milky Way. Black holes spin because of a principle called conservation of angular momentum. You've seen that principle in action if you've ever watched an ice skater spin faster as they pull their arms closer to their body. A similar thing happens with black holes. Most black holes start out as the collapsed cores of massive stars. Those stars have some small amount of spin, and as the center collapses into a black hole, that spin gets faster. Except with black holes, there's a little catch. For a given mass, there's a maximum speed. If a black hole has too much spin, it will actually release some of the energy in its system until it slows down to below that limit. So rather than saying that a black hole rotates however many times a second, astronomers assign it a so-called spin parameter. That gives it speed as a percent of how fast it physically could spin. The current prize holder, as of January 2019, is rotating at between 92 and 95% of its speed limit. So it might not be the fastest spinning black hole ever, but so far it's the one spinning closest to its physical limit. Astronomers can't measure a spinning black hole itself, of course, so they rely on clues in the light around it. But actually measuring a black hole's spin is pretty complicated, since there's a lot of light interfering with the signal. As a result, astronomers only have accurate measurements for half a dozen black holes with really high spin parameters. Meaning, again, this title could be up for grabs. But as our technology improves and we find new record setters, these extreme black holes will keep giving us ways to test our predictions about the limits of physics and reality as we know it.
So that's the birth and life of some awesome black holes. But black holes aren't just our cool space neighbors. As you might imagine from their name, black holes have a dark side. They have the power to consume everything around them. So here is how black holes can overpower stars. Black holes are one of the most extremely dense objects in the known universe, but even they can level up. Within the hearts of the largest galaxies, you can find black holes with masses exceeding 1 billion times that of our sun. And a fraction of these these has superpowers all their own, like driving a cosmic engine that outshines the rest of the galaxy, and even serving as birth control for stars. In the late 1950s, astronomers began matching point-like radio signals in the night sky with optical signals coming from the same spot. That visible light was also a point, like all the stars we're used to seeing, but when astronomers split up the light into its different colors, they noticed that the combination of colors did not follow the pattern for any known type of star. So astronomers called them QSOs, quasi-stellar objects. They're commonly known today as quasars, short for quasi-stellar radio sources. Well, it turned out the light looked different because the quasars were far away. They were very far away, far enough that the universe's expansion could noticeably stretch out the light waves on their way to us. The amount of stretching could tell us these quasars were billions of light years away. So in order to be visible to us, a quasar would need to be super bright, up to thousands of times brighter than all of the starlight in an entire galaxy. An impressive feat considering that some of them are as small as a single solar system. Scientists did eventually learn how all of this is possible. A quasar is a type of active galactic nucleus, or AGN. To make one, you need a supermassive black hole at the heart of a galaxy that is actively slurping up matter around it. All that matter gets heated up through friction as it spirals down into the black hole, becoming so hot it starts to visibly glow. But because that black hole engine is so powerful, the effect is a bit more intense than what you see happening in the coils of your space heater. The brightest quasar we've found so far is as bright as 600 trillion suns. But being bright isn't good enough for these guys. Between 20 and 50% of AGNs produce a kind of space wind astronomers call outflow, where light and other particles are thrust out in all directions from the quasar at the center of the galaxy. Well, the next question was how much of an influence this outflowing material could have on the rest of the galaxy. Like, could it redistribute energy or matter so much it prevented a bunch of baby stars from forming, or actually make a bunch of new baby stars? Astronomers have been looking for an answer for decades, and just a few years ago, the jury was still out. A series of papers published in the Astrophysical Journal Supplement series back in 2020 has thrown some additional data into the ring, focusing on a narrow range of light we get from quasars, high-energy UV wavelengths. These wavelengths are formed after the outflow smashes into the matter around the galaxy, raising temperatures billions of degrees. That means a lot of the light these outflows emit is in the ultraviolet and X-ray part of the electromagnetic spectrum. The team behind these papers wanted to investigate both how fast these outflows were moving through the galaxy and how far they extended from the galactic center to determine if an AGN had an effect on its galaxy. To get those measurements, they collected the spectra of 10 different quasars across several years using the Hubble Space Telescope. Spectra are like chemical fingerprints. Dips in the signal at different wavelengths of light, called troughs, correspond to different elements flowing toward us and away from the AGN. Hubble provided clear signals from quasars up to 9.4 billion light years away, and the super high-energy UV part of the spectrum has way more troughs to analyze than longer UV wavelengths, while also covering about 90% of the matter in the outflows. Across 7 papers, the team reported a number of results. In one case, studying 13 outflows from 4 quasars, they found that 9 of those outflows had extended anywhere from 326 to 6,523 light-years beyond their galactic centers. Although that outflow is smaller than what a galaxy measures across, they are still bigger than what quasar models previously predicted. In another paper, they report on the same outflow but measured twice about 3 years apart. They found that the outflow accelerated up to around 21,000 kilometers per second. That's around 74 million kilometers per hour. And they conclude that this new data suggests a quote-unquote large fraction of outflows produce AGN feedback, which means that AGNs influence how fast stars form in their galaxies. In this case, the gas that would have otherwise been cool enough to collapse down into baby stars suddenly gets too hot to handle and has to cool down all over again for them to form. But the outflows can also push matter away. One of the astronomers even said it's equivalent to hundreds of our suns in gas each year, which could literally starve stellar nurseries of the material they need. But the debate on outflows and feedback isn't settled completely. 10 quasars is a tiny sample size, especially compared to the millions we've cataloged. New telescopes like the James Webb Space Telescope will provide even better optics that will allow astronomers astronomers to view these distant beads of light in even better detail. Okay, so black holes are the ultimate space eaters and space heaters. They kind of win at space, so when everything else in the universe dies, they may be the last things left. And the question is, will we be there to see that day?
Modern humans evolved a couple 100,000 years ago. And between ice ages, volcanoes, climate change, earthquakes, droughts, floods, and Reddit being down sometimes, we've seen some stuff. But on cosmic timescales, 200,000 or 300,000 years is just a drop in the bucket. The longer we're around, the more likely we are to witness something truly earth-shattering, whether metaphorically or literally. And someday, if we're still here, we'll have to face things like Earth melting as it's engulfed by the sun, or the sun going out, or galaxies colliding. One way or the other, we're going to have to leave home if we want to survive. And even if we had fancy starships, how long could we actually outrun extinction before the universe became uninhabitable to us? It's such a big question that we've made a special extra long episode about it, because the answer is a surprisingly long time. Now, to be clear, we probably won't have to leave home anytime soon, so there's plenty of time to get our spaceships ready. Like, we might hear a lot about climate change these days, but no matter how destructive or disruptive it is, researchers don't think that it will threaten our entire species. There are plenty of variables to consider, but overall the odds are pretty good that we'll get through it one way or another. The same goes for one of the internet's favorite doomsday scenarios, a supervolcano. Even though that would be rough, it probably couldn't take us all out. There are just too many people spread throughout the world. But we will have to leave Earth someday. Because even if we dodge a huge asteroid impact or the takeover of artificial intelligence, our planet will eventually stop being habitable, thanks to the sun. The sun brightens as it ages, and generally, that will make Earth warmer over the next few 100 million years, which will cause all kinds of problems. For example, rocks tend to erode more easily at higher temperatures, so in the future, more new rocky surfaces will be exposed to the atmosphere than today. Exposed rock can react with carbon dioxide, so the more exposed rock there is, the less CO2 will be left in the atmosphere. That might seem like a good thing given how worried we are today about climate change, but remember that plants need CO2 like we need oxygen. And according to some estimates, in about 800 million years, there actually won't be enough of the gas left in the atmosphere for photosynthesis. If those estimates are right, that would be the end of all life on Earth bigger than a bacterium, and they'd go extinct about 1 billion increasingly warm years later. Future people might prevent this by building something to block the extra sunlight. Or they could use repeated asteroid flybys to gravitationally inch Earth's orbit away from the sun. But they might also decide that Earth just isn't worth it anymore and could leave. The most obvious option would be to go to Mars, since it's closest. We'd still have to give the planet an atmosphere and a livable temperature, but with a dash of terraforming, we'd be fine. Although Mars still won't be a permanent solution. 5 or 6 billion years from now, the sun will finally start running out of hydrogen fuel in its core. After that, it will fuse helium and it will start growing. First, it will engulf Mercury and then Venus, and 7.6 billion years from now, its outer layers will probably pass through Earth's orbit too, likely destroying almost everything we've ever built. The people on Mars wouldn't be much better off either. Mars will never fall into the sun, but it will become too hot to be comfortable for life. And with the sun so much closer, solar radiation will rip apart any Martian atmosphere our descendants tried to create. But we wouldn't be out of options yet, because while the sun balloons, the outer solar system may have it pretty good. Jupiter's moon Europa and Saturn's moon Enceladus are both ice-covered today, but they'll heat up as the sun expands and will eventually become water worlds. And briefly, we could live there. But again, that wouldn't last forever. In fact, we might be on the move after as little as 100,000 years. Once more, because of the sun. Around that time, the sun will have expanded so much that its outer layers will finally escape into space, leaving behind a tiny white dwarf star surrounded by a big cloudy nebula. Comparatively speaking, white dwarfs don't emanate much energy, so the newly minted one at the center of the solar system will leave the remaining planets and moons as cold as interstellar space. And without a good heat source, there's no usable energy, so any civilization that's still around we'll have to move on. By this point, though, we'll probably just fold our Dyson sphere into overhead compartments and head off to colonize some other planetary system. Because hey, if we haven't figured out interstellar travel in 7 billion years, well, we'll have a problem. But let's assume we figure it out, and don't spend the next forever binging Netflix. Today, the closest star is Proxima Centauri, which is about 4 light years away. It's a red dwarf star, which means it will likely outlive the sun, and it already has a potentially habitable planet. But since red dwarfs also emit some seriously dangerous flares every now and then, it might not be our best choice. Besides, current estimates suggest that there are billions of planets out there that could support water, so we have plenty of other options. Which is good, because today, there's really no way of knowing where Proxima Centauri will be that far in the future. Stellar orbits in the Milky Way naturally get rearranged over billions of years, so Proxima Centauri might not be our closest neighbor anymore. Also, and maybe more importantly, the Milky Way won't exactly be a thing in 7 billion years. It will probably collide with the Andromeda Galaxy even before the sun expands into the inner solar system. Or, at the very least, they'll pass close enough to each other to cause some chaos. Thankfully, there's almost no chance of stars actually smashing into each other since stars are just too spread out. But the collision will make long-term wayfinding tricky. Stars will be thrown all over the place, while the new galaxy, known as MILKY, takes shape over billions of years. Yes, that is the real proposed nickname, and no, I don't support it. So maybe the next star we'll go to hasn't been discovered yet. Or born. And even if we do have the technology to leave the solar system, we'll have to watch out for the dangers of interstellar space. For example, we'll have to keep an eye out for supernovas, since colliding gas clouds will produce lots of enormous short-lived stars that explode at the end of their lives. And radiation from those explosions could easily wipe us out mid-journey. But if we do learn to safely travel to new stars, that would allow humans to keep thriving for a long time. We're talking trillions of years. Because even when our new home star goes out, we could hop over to another system. As a bonus, the formation of MILKY will also make a good number of smaller, longer-lived stars like our sun. So we'll have a lot of options. But even though trillions of years is an unimaginably long time, it's not forever. Eventually, all the sun-like stars in the universe will wink out, one after another, and there won't be enough big clouds of hydrogen-rich gas left to replace them. But even then, that won't be the end of humanity. Our corner of space will get darker and cooler, since it will be lit mainly by tiny, long-lasting red dwarfs. But we could still survive around them, like our ancestors huddled around their flickering campfires. We would have to find a way to live with the violent solar flares, though. Or, if nothing else, we would have to find a way to harness the red dwarf's energy without being in the range of those flares. But assuming we figure that out, we'll be able to stay alive long into the future. Eventually, though, even those stars will die, along with any remnants like white dwarfs. And finally, the universe will be black. At this point, our only decent source of energy will be black holes, since there will still be plenty of those floating around, with gas falling into them all the time. If our descendants are surviving on homemade nuclear fusion power, which seems likely considering all the stars will be gone, they'll need that gas to keep making energy. Of course, with black holes gobbling up that gas and the expansion of the universe spreading it out more and more diffusely, it'll be hard for them to find enough fuel. There will always be the odd proton or dead planet gliding through the vastness of empty space that we could somehow harness resources or energy from. But just about everything else is eventually going into a black hole. Fortunately, it will take a while for black holes to vacuum the universe, and that's putting it lightly. For you fans of metric prefixes, astronomers estimate that it will be about 1 billion yada years before there's pretty much nothing out there but black holes. That's 1 billion trillion years, or a 1 with 33 zeros after it. And I think we can agree that's a long time. Many physicists who are trying to combine everything we know about the universe into a single elegant idea think that, coincidentally, protons will decay after about this much time too. And that would definitely be the end of all life. But if they're wrong, physicists and mathematicians have found that even in that dark black hole-filled universe completely devoid of raw materials, life could still persist. They've discovered that if you dive close enough to a spinning black hole and drop something in it just the right way, you can steal energy from the black hole itself. The exact mechanism for how it works is pretty complicated, and at the end of the day, no one is totally sure if you could power a civilization this way. But for now, we think it's still an option, and we have time to figure out the details. Then again, black holes aren't forever either. In 1974, Stephen Hawking published his discovery that black holes very, very slowly radiate energy in a process now known as Hawking radiation. Hawking radiation is incredibly weak for any reasonably large black hole, so it's not like we could use it to heat our space colonies. But the important part is that it causes black holes to slowly shrink. And after almost a Google years, that's a 1 with 100 zeros after it, even the biggest black holes in the universe will evaporate due to Hawking radiation. After that, it's hard to imagine any kind of life flourishing. There won't be many atoms left, and any energy will be so uniform that we won't really be able to do anything with it. This is known as the heat death of the universe, and it's how today's best cosmological models predict the universe will finally end. Even here, though, there may be the tiniest glimmer of hope. In 1979, the physicist Freeman Dyson, the same guy who made Dyson spheres famous, imagined an organism that worked kind of like a computer. When it's on, it uses energy to think or do something, and when it's sleeping, it does essentially nothing. Dyson was able to show that by sleeping longer and longer between each pair of thoughts, the organism could live an infinite amount of time, but only ever use a tiny bit of energy. So with a big enough battery, this thing could last forever. And that brings us to our final thought. By this point in time, humans might not technically be humans anymore, thanks to evolution. In fact, we might have changed so much that nobody will remember that time when we had 10 fingers and breakable bones and disease. Realistically, that day could come much sooner than trillions of years from now. So maybe we could become, or even choose to become, this weird species that waits a quadrillion years between thoughts. Maybe we'll decide that that's worth immortality. Or maybe we'll just decide we've lived long enough. But hey, we have a long time to sort out those decisions. In the meantime, the best thing we can do is keep taking care of the planet we have so we can make the most of the next 800 million years. Because ultimately, scientists can tell us a lot about what the universe will be like in the far-off future, but as for what humans will do until then, well, that's up to us.
The universe is born, black holes eat everything, and then the universe dies. What an easygoing existence you'd have if you were just a black hole. Just exist and eat until the end of time. But until then, we've got some more SciShow space to help you pass the time. If you thought that these black holes were extreme, check out this video of the most extreme planets in the universe. Thank you for watching this video.